Okay, so thanks for the introduction, and today it's my honor to present to you our work on kernel quantile embeddings and associated probability metrics. This has just been accepted at ICML 2025, not quite on archive soon, but I put it on my website so you can go check out the details. And yeah, I'm in the 4th year of my PhD, finishing up before spring next year, and yeah, I'm interested in kernel NGP theory and in particular applications in biology. And this is work with my great collaborators, Silun Chow, who goes by Alan sometimes, FX Briol, my supervisor, and Krikamo Moentet. And bulk of it was completed when I visited these two guys in Saarbrücken, which is it's a nice environment. You all should go. Okay, so many tasks in statistics and machine learning rely on representing and comparing probability distributions. And this is the problem that we'll be looking at in the talk, representing distributions and then comparing the representations that were obtained. And yeah, this setting is ubiquitous. It appears in problems in hypothesis testing, parameter estimations, causal inference, feature attribution, learning distribution, among others. I'm sure there's many, many more. And a successful and commonly used way of constructing these representation has been mapping the distributions from some input space X onto functions in a reproducing kernel Hilbert space calligraphic H here, which is a space of functions which have a certain nice structure. If you haven't encountered RKHS, it's just suffices to say they have a nice structure and they're induced by a certain function of two variables called a kernel. So to construct these objects called kernel mean embeddings, we do a two-step process. One, getting a distribution of the kernel where one parameter is distributed with respect to the input distribution of interest, and then taking an integral over that object, getting the mean of k of x over p. And the resulting function of x is called the kernel mean embedding of the distribution p. This naturally creates, since RKHS is an inner product space, this naturally leads us to a, I'm going to say, discrepancy between the distributions, which is just measuring the distance between the kernel mean embeddings in the RKHS. And this discrepancy, called maximum mean discrepancy, is a distance for a class of kernels called mean characteristic. In the literature, they're called characteristic, but for the context of this talk, we'll be talking about other types of characteristicness, so I'm going to call these mean characteristic kernels, which are kernels for which this mapping is injective, and thereby MMD is a distance. A couple of words on that. The sufficient conditions under which a kernel is mean characteristic are well understood for Euclidean spaces and bounded and translation invariant kernels, and can be challenging to establish outside of this setting. For example, it's known that many kernels used on graphs are not characteristic. And as I said, this can be thought of as a two-step process of getting this distribution in the RKHS and then taking the mean. And of course, one might wonder, well, what if I took some other summary here, not just the mean, some nonlinear operator that summarizes the distribution in a different way? What is there utility to that? So this is a relatively underexplored space, primarily because the linearity of the mean makes it convenient to work with. But this gap has started being addressed recently, where people looked at cumulants and variances and median. And we basically contribute to this line of research and propose representing distributions with a construct that we call kernel quantiles of P under kernel K, and I will go explicitly into what we mean by kernel quantiles. And based on these kernel quantiles, we suggest kernel quantile discrepancies that can be used to compare distributions that are distances under mild conditions, that are connected or rather collapse in a certain setting to Wasserstein distances, and can be estimated at near linear cost. Okay, so we heard a lot about quantiles already, so I'll just go over this quickly. When the input space, for the purpose of the slide, it's not the input space, it's just space. When the space X is one-dimensional, the alpha quantile of P is defined as the smallest element in the space for which the measure of minus infinity to X is at least equal to alpha. And, oh, okay, something is wrong here. Sorry, there is a problem with the slides, but, I think I have a solution. When you render from Keynote, sometimes things get funky. And this what, oh no. Okay, let me just check that everything else is fine. Okay, everything else is fine. Okay, then it just happened here. All right, so what was what was supposed to be here is an error with an alpha here, and I want to say that if this is the CDF of P, then if the CDF is continuous, then the alpha quantile is just the inverse of the CDF, and more generally, it's this infimum function. As has been covered, when X is in a d-dimensional real space, there is no longer a default ordering on the space, so there are multiple extensions to quantiles. We've heard a lot about them in the first talk of the day with the notions of data depths, which is a related notion to extending quantiles. And here we consider specifically directional quantiles. So this is how directional quantiles work. Suppose this is, let's look at an example where X is a subset of R2, and this P is a measure on X. Say this is a unit circle on X with a, apologies, with an element U on the unit circle. To get the directional quantile in direction U, I'm first collapsing all the projecting, not collapsing, I'm first projecting the...
Excuse me, what is the center of the circle? Mm-hmm. Is it the
zero.
Mean?
No. The center here is just zero. But this is I'll talk about that later. Okay. For now, it's just the origin of the space. That's an extremely valid question, but yeah, this is the origin of the space for now. Yeah, so we're projecting the distribution onto the direction U to get now a one-dimensional distribution in the direction U, and just take quantiles in this now one-dimensional distribution defined the regular way. And if we continue this process for every U on the unit sphere, we may draw quantile contours that will look something like this. Here, the degrees represent different directions in R2. Formally, this is what that looks like. A quantile of P, an alpha quantile of P in direction U, where U is on the unit sphere, is the regular one-dimensional quantile of the push forward of P under the projection map. The projection map is these little arrows that just project onto U, times U, the direction. And one may notice that in this construct, we never really used any Euclidean structure here, other than the inner product. And this extends naturally to infinite dimensional Hilbert spaces, or Hilbert spaces of arbitrary dimensionality. Provided we can do inner product, we can build directional quantiles within the space. Towards the question about what this point is, I said the origin. For the sake of this talk, I will keep it being the origin, but in the paper, we consider two versions of quantiles, a non-centered version, which is this guy, center is the origin, and a centered version, where this is the mean of the distribution, and we do directional quantiles around the mean, and then subtract the mean to compensate for this. We can talk about that later. I can point you to the paper where, yeah. But yeah, for the sake of this talk, this is just the origin. Regarding invariances, this version, non-centered quantiles, respect scale invariance and shift invariance. No, scale invariance and rotational invariance. They do not respect shift invariance, but since I'm jumping ahead quite a bit, but since we ultimately will be using these representations to compare two distributions, lack of invariance once the shift does not matter, because with the shift, it all shifts by, it's really happy, okay.
Yeah.
This is the connection.
Yeah. Oh, okay.
Okay.
Yeah, okay, great. Let me go back. The change in the equality for shift invariance still leads to the shifts canceling out if we consider differences between distributions. So lack of shift invariance in the classical sense doesn't particularly matter. And for the second version, shift invariance is observed in the classical sense. Anyway, sorry, these were details. Okay, so this construct extends to arbitrary Hilbert spaces, and motivated by this, we suggest kernel quantiles, which are now, unlike on the previous slide, where the distribution and the quantiles lived in the same space. I would say, let's say I have a distribution P on some space X, of which I know nothing other than the topology and the fact that I can define a kernel on it. And I'll be building quantiles in the RKHS of the kernel. And then they will be useful, as I hopefully will manage to convince you. Okay, so we're representing now the distribution P with a set of what we call kernel quantiles, which are quantiles in the reproducing kernel Hilbert space of K of this distribution, thanks to a reproducing property in the RKHS. Again, if you're not familiar, it doesn't particularly matter. Because of this property, we recover this form for these quantiles. So we say that an alpha kernel quantile of P in the direction U, where U is now a function on the unit sphere in the RKHS, is the regular one-dimensional quantile of the push forward of P under U. Remember that U goes from X to R, so this is just a regular one-dimensional quantile times U. So this guy is a function. It's like a scaled version of U. And if these are built for every alpha and every U, that's what these contours are meant to visualize. So let's say this is alpha 0.5, 0.2, 0.5, 0.7, and like in all directions U. Yeah, again, measure P lives on the input space X, not in the RKHS. This is a subtle but important difference because it allows us to require no structure in X other than the kernel. Now, of course, since what we're ultimately interested in is comparing the distribution for the purpose of this talk, my immediate question is, well, is this construct injective? If I have two P and Q that are different, can I say that I don't collapse them into the same set of quantile contours? And it turns out that the answer is yes, under very mild conditions, which is great. And we'll call kernels for which this mapping is injective quantile characteristic, analogously to mean characteristic kernels for kernel mean embeddings. Okay, specifically, this is what these sufficient conditions look like. If the input space X is sufficiently regular, which is Hausdorff separable and sigma compact, where Hausdorff means it can separate points, separable, there's a countable dense subset, and sigma compact means it's a union of a countable number of compact sets. As an example, all Polish spaces satisfy this, and it's slightly beyond the Polish spaces. And if the kernel K is continuous and separating on X, meaning for any two different input points, the K of X and K of Y as functions of this dot thing are not identical. As an intuition, if this is not satisfied, then trivially no RKHS embedding can differentiate between Dirac deltas centered at X and Y. So this is quite crucial to use any sort of kernel method, unless we don't want to compare Dirac deltas. If the application of interest is something more general than this, we can drop the separability and sigma compactness at the minor cost of restricting the characteristic property to only the radon measures, which are Borel measures minus the really strangely behaving stuff. So yeah, if you want to drop separable and sigma compact, we have to be content with just looking at radon measures, which hopefully is okay. Yeah, so under these mild conditions, we have that K is quantile characteristic, meaning the mapping from the distribution to the whole set of quantiles is injective. And like I said earlier, K's mean characteristic is more challenging to establish in general. We have sufficient conditions for Euclidean spaces, bounded kernels, translation invariant kernels. This is a and list. But in general, it's challenging. And this leads to a natural question: can I say that quantile characteristicness is more general than mean characteristicness? Or is it just that this is a hard object to analyze, it's great, but it's just hard? So turns out we can say something about this. In fact, we have this following result. If K is mean characteristic, then K is necessarily quantile characteristic, but not vice versa. So this means that if a kernel K can separate distributions through kernel mean embeddings, then it can necessarily do that through quantile embeddings as well. And the opposite doesn't hold. An example of the opposite is a polynomial kernel. If you're familiar with kernel theory, you may know that MMD under polynomial kernel is essentially just comparing the first M moments. The polynomial kernel is of order M, so not characteristic if the two distributions are identical in these M moments and different after that. And yeah, polynomial kernel is quantile characteristic because it satisfies all of those minor conditions that I listed earlier. And this result in particular leads to this powerful implication that for any discrepancy D that I'm building on top of the quantiles, so long as it aggregates the quantiles in an injective way, meaning it doesn't take two different sets of quantiles and collapse them to zero, I will have that if MMD is able to differentiate between P and Q, then so can D, and not vice versa. This is a polynomial kernel example.
Can I ask like a silly question?
Yes.
I've been a bit lost in your definition of your O alpha P U.
Definition of.
Yeah. So
Yes.
why do you multiply? What's the idea of what's the intuition? Why do you multiply by U of X? What's the intuition of it?
Okay, so frankly, we can get rid of this multiplication and just work with a real representation. Yeah, that would also be fine. We wanted to keep consistency with prior work on multivariate quantiles where they multiply by U. like frank. Oh no, sorry, there is a second good reason. I'm just I got too into this talk and forgot about the second good reason. Second good reason is that if we do a standard version of quantiles, which is not in this talk because I thought I only had 30 minutes, where we shift by the mean and add the mean back, we need a functional form because otherwise we can't operate easily with the kernel mean embedding. It's a little hard to describe hand-wavingly, but for the sake of centering, yeah, that's a big reason. For the purpose of this talk, yeah, we could have cut out U and everything would have stayed the same.
And so can I go on?
Yes, yeah.
And so then, so the injectivity you're considering is that you're varying alpha and U, or you're
Yes,
fixing alpha
yeah,
and
yeah.
U,
Yes, both are varying. We are mapping from P to this entire thing.
All right, okay. So
Yeah.
it's both alpha and U.
Yeah. I know that this seems like da, of course, it's obvious. It seems like just a if we were in d dimensions, this would just be the Cramer-Wald theorem, and we have it immediately. Cramer-Wald extensions to Hilbert spaces are challenging and require a whole list of conditions, but for a KHS, it's really nice. So, yeah.
So just to get into, again, sorry, I'm just asking you another question, but I want to get the intuition of it. So the reason why somehow the condition that you get for the injectivity is it due to the fact that you have this sort of alpha as well? Somehow it's not only U that you're spanning over, but it's also alpha, and so that gives you some extra condition in a sense?
Yeah. So this condition is basically saying if I have an expressive enough family of functions with some conditions on the family, and the push forward of my measure with these functions, the push forwards of my two measures with these functions for each of these functions is the same, that means that the measures must be the same. And then measures being the push forward is an R, and push forward being the same and quantiles being the same is the same thing, because quantiles fully represent the distribution. So the result is, if you get into the proof, it's less about the quantiles are like the last step. You're like, oh, they're identical in R, then the quantiles must be identical. Yes?
Since you are looking at the slices with respect to these RHS functions, so do you have like a closed form, like in the case of MMD?
We do not have a closed form like in case of MMD, no. But the closed form in case of MMD still requires estimation on top. And I will lower down the top, propose an estimated that works well and competitively with MMD.
Actually, in your next slide, you looked at this the kernel being separating. That's a much, I mean...
Not mean separating.
Yeah, so that one is like the kernel being strictly positive effect. Right, so this is like a much weaker condition than universality or characteristic property.
Sorry, what did you say?
So this is a much weaker condition than the kernel being universal or characteristic.
Yes.
So you're saying, so of course this condition does not imply
universality or mean characteristicness.
For your MMD.
No, polynomial kernel is an easy example. It meets both of those things, and of course it's neither universal nor characteristic.
Okay. So here you're claiming that even a weaker condition is sufficient for your kernel to be quantum characteristic.
Yes. Any more questions since we're here?
Can you just take a linear kernel or bilinear kernel?
Linear kernel. I'm thinking. I mean, again, jumping ahead for the linear kernel and with some extra stuff, and X being RD, this collapses to sliced Wasserstein. So, yes. sorry, what I said was probably not helpful. Yes, linear kernel will it always satisfy this? Yeah, yes, yeah, you can take the linear kernel. And what I said earlier, well, when we get to this slice Wasserstein, maybe it will be helpful for linear kernel and under some extra things. The discrepancy that we build collapses to sliced Wasserstein, and we're not surprised by sliced Wasserstein being a distance. So that's an intuition for this, maybe.
Maybe one more question for this slide. So you mentioned Hilbert spaces, but they are not sigma compact. So what's the
Input space, sigma contour, not the Hilbert space.
X.
X. Yeah, let me go back. Yeah, so on this picture, X is the input space, and RKHS is what we're mapping from X to. But yeah, again, I know that that's not what your question was about, but if you're interested in removing sigma compactness, you can, and then just work on Radon measures.
One more question about understanding the big picture. So, is it about the fact that your push forward are characteristic in the sense that the kernel that you get by pushing your measure, the kernels that you get by focusing on one-dimensional spaces is characteristic, and so you can basically come back. So if you take any U, you fix U, then you can get the push forward measure. You can identify it.
The big picture is that there's a lot of U. The RKHS
Exactly.
is big. Yeah, so we are comparing across many things.
But basically, if you take your measure, you push it forward, and you can identify the measure, the projected, the push forward measure for any U.
Yeah.
Yeah.
Yes.
So you get the notion of characteristicness on the rim line that is kind of hidden. I mean,
The
probably
notion-
it's another set of sufficient conditions that could be. Yeah, it's the alpha story.
Is the what?
The story with alpha is that basically you can get the marginal distribution, you can get the projection, the distribution of the projection for any U. You can come back to the marginal distribution or to the projected distribution, and so since you can do it for any U, you can do it for the.
Yes, yeah. You can see it like that, like we are slicing, like we're taking U marginals. I'm doing air quotes because I know that that's not a concept. It's like we're taking U marginals for a very large number of U. Yeah.
Sorry, one more question.
Yeah, no, absolutely. Thank you.
Sorry.
Your kernel being continuous, does it rule out some type of spaces? I don't know, infinite dimensions, for instance, or what does it do?
It's a very good question. What does it actually do? Okay, so the honest answer of what does it do is it allows me to. Is it the
Yeah, it's the
global?
cable.
Ah, yeah. Okay. Oh, now it's small. Let me go to. No. Yes. The honest answer is that K being continuous allows me to use a result on characteristic functionals, not functions, functionals, that says that if a characteristic functional on a family of continuous functions that are separating in the vector space, that's all that it requires. If the functionals match on that, then the distributions match. Now, I don't know why that result requires continuity. I can go and check. That's a very valid question. Do you know why?
No, I'm just thinking there is probably a way to formulate another set of
There's,
conditions.
yeah.
And continuous is
There
probably
may be.
just something
That's
small.
very.
Yeah.
Are you interested in non-continuous kernels, or is it just a general?
Yeah, the type of spaces that I work with are exactly the ones where they are not. So, yeah.
I can look into that after the talk. It's possible
Yeah,
that proof allows for extensions. I honestly didn't look at the proof of that result. More questions? Okay, we go through that. Okay, implication that any discrepancy that aggregates quantiles injectively, we have that if MMD is able to tell P and Q apart, then so can D, and not the other way around. And being able to tell distributions apart is the key property of a distance. So we're like, this is great. And next step, we're going to build a specific family of such discrepancies and suggest estimators for them. Yeah, okay. And the recipe would be for every U, we aggregate the quantiles and then do an aggregation over U. And if both are injective, then we're basically done. I would normally pause here for questions, but we just had a session, so I will move on. Okay, step one, aggregating over quantiles. We suggest the following notion of a directional difference in direction U, where remember U is a function in the RKHS of norm1, function in the RKHS unit sphere. And to aggregate over all of the quantiles, we integrate over the differences between quantiles of P and Q in this chosen direction U. Over some importance measure over quantiles. By default, we can pick nu to be uniform over 0, 1, which is just saying all of the quantiles are equally important. If we have some belief into upweighing or downweight extreme values, nu can be chosen respectively to upweigh or downweigh the extreme quantiles. A little pictorial intuition of what this might look like. The first two boxes here are very loose, for the sake of the intuition, representation of two functions on the RKHS unisphere, U1 and U2. On the top here, I have two distributions that I'm comparing, P and Q. And the idea here is that under, let's say, under U1, P and Q are really well separated. They probably have all of the different quantiles except for the tail ones. And under U2, P and Q are looking very similar, and they may be differing in the tails. So the opposite scenario to what's happening with U1. And under this setting, the object under the integral here, the difference between the quantiles. And yeah, to an earlier question, if we weren't multiplying by U here, we would just have an absolute value between quantiles. Yeah, in this setting, this difference for the case of U1 might look something like this, where, well, it probably should have been lower for the 0 quantile, but yeah, probably should have gone like this, where it's small for the extreme quantiles and larger in the middle, representing the difference between these two guys. And for U2, they might be super different in the tails and look very similar for the quantiles in the middle. And we would be integrating U1 over nu and U2 over nu. Yeah, so this is an example of what's happening with this directional difference object. And now step 2, we aggregate directional differences over all U on the unit sphere of the RKHS. We suggest two modes of aggregation, an LP1, where we're taking an expectation over U sampled from some measure over the unit sphere, with some power things to preserve it being a distance, and a supremum type of aggregation where we just take a supremum over all U on the unit sphere. Now, one might say that, well, clearly this is more differentiating because we are considering all of the directions equally. Sorry, because we are considering all the directions, so clearly this is better, but the optimization required to approximate the supremum here is complicated. So further down, we will be focusing mostly on this object, mainly to avoid optimizing for the supremum here. But there are people who did something very similar to this, and I will be covering this later. Okay, so these are the discrepancies essentially, the expected version and the supremum version that both do aggregation over alpha and then aggregation over U. And what was the thing that we were interested in? Are they distances? Recall that we had these minor conditions under which K is quantile characteristic. And when the quantiles are aggregated injectively, we get a distance, provided K is quantile characteristic. And we can assure the injective aggregation for the supremum distance, provided nu, the measure of a quantiles here, has full support in 0, 1. Intuitively, this is clear because if nu didn't have full support over 0, 1, it would be dropping some of the quantiles. So even if K is quantile characteristic, well, we just lost some of the quantiles, so what good does it do? So provided we don't lose any of the quantiles, meaning nu has full support in 0, 1, this supremum KQD is a distance on a set of Borel probability measures, and the thing I alluded to earlier where we can drop some assumptions on X and then work on Radon probability measures, yeah, that's where it would happen. Yeah, we can have even weaker assumptions on X and then say Radon here, if that's valuable for your application. And further and very similarly for the expected version of the distance, if gamma, the measure over the unit sphere, has full support in the unit sphere, same logic, we shouldn't be dropping any directions, then EKQD is also a distance. And this is a direct consequence of quantile characteristicness. Really nothing special going on here. I think this is, oh, okay. Other questions at this point?
Do we know if they're sort of equivalent to the weak convergence, or do they neutralize the weak convergence? Or?
I didn't look into it. I suspect that one would be able to establish this because of connections to Slice-Wasserstein that I will go over on this second slide, but I have not looked into this. Connections. If I write out the expected KQD and the supremum KQD explicitly without resorting to directional quantiles, you can see that this is a power P difference between quantiles integrated and then either average or supremum taken over the slicing directions. And for those familiar, this is recovering sliced and max sliced Wasserstein distances when X is RD, K is linear, and nu and gamma are uniform. And more generally, when nu is uniform and nothing else, both KQD distances can be seen as kernelized versions of Slice-Wasserstein and max Slice-Wasserstein, where kernel Slice-Wasserstein is a new concept. To our knowledge, it hasn't been considered. Kernel max Slice-Wasserstein was introduced in this paper here, where they proposed an estimator for this of complexity n cube log n. And yeah, so yeah, now we'll be considering estimators of expected kernel quantile discrepancy, primarily because we want to avoid the complexities of optimizing for the supremum. But if you're interested in that, there is a paper that considered it, and their estimator can be used beyond uniform nu, so that would be fine. Okay, so estimators, what makes EKQD usable? Suppose I have n samples from P and Q, and this is extendable when the number of samples are different, but for the simplicity of presentation, I picked the number of samples the same. And I'm denoting Pn and Qn as empirical versions of P and Q based on these samples. Suppose I pick some measure gamma on the unit sphere, we'll go into that in a little bit, and have L samples from gamma. Then expected kernel quantile discrepancy between Pn and Qn with measure nu, with density f nu, and the measure gamma L over the unit sphere takes this exact form, where we are summing over all directions and summing over all quantiles, and this approximates the difference between quantiles and weighs them with the nu of choice. This object here is the jth order statistic. That is just j smallest element of ui of x1 to xn, and it's an estimator of this quantile, of j divided by n ceiling quantile. So basically summing over n quantiles. That's what's going on here. And this guy can be used as a plug-in estimator for EQQT between P and Q. And we can show that it's consistent and finite sample consistent. And I'm not going into this, but there is more results on this in the paper. Now, of course, picking a gamma is a design choice. This isn't something that's given by the problem. It's a self-inflicted damage here, where we said that our method requires some measure gamma on the unit sphere. Picking a uniform might seem like an immediate choice, but of course there is no uniform distribution when the RKHS is infinite dimensional, and most interesting RKHS are infinite dimensional, so we can't have a uniform gamma. Instead, we suggest a projected Gaussian gamma, meaning it's a projection of a gamma prime that's Gaussian on the entire RKHS. And we suggest a sampling scheme under which the estimator has complexity of n log squared n for this choice of L. And in experiments, we showed that this is competitive against MMD estimators of comparable cost. Before I go to experiments, are there questions about it? Yeah.
So when you say projected Gaussian, so because this is a measure defined on the infinite RKHS, how do you pick your covariance software?
The covariance is the integral operator of the kernel under some reference measures. Do you want me to write
How
it?
do you pick the reference measure?
Sorry?
How do you pick the reference measure? So
Very interesting question. Let me just write what they... And then gamma is okay, yes, this is the reference measure mu. In the experiments that I'll show you, we just take it to be Pn plus Qn divided by 2. So we just assume the most general setting where we have nothing from the input space other than these samples. No? Okay. I think I should just keep going back and forth. But in response to reviewers, we also ran some experiments where when we do have some reference measure on the input space, like standard Gaussian or uniform, where we use mu to be that measure. And in that particular one set of experiments, reference measure performed slightly better, but I don't know how representative that was. But yes, we consider, in the experiments that I'll show, we consider the most general case where mu is Pn plus Qn divided by 2. Yes.
I was wondering, so you choose L equals log n, but then that's a very slow convergence rate to your expectation.
Yes. So we have a. No, that was a bad call. Yes, because of this double sum, we'll have a convergence of the order log n to some power plus something. It does mean that, so for L chosen to be something proportional to n, like n divided by log n or something like that, we recover convergence of MMD. But yes, for the estimator studied here, the theoretical convergence rate is not great. Yeah, so it's likely trade-off between convergence guarantees and computational cost. Any more questions? Yes.
Suppose if you want to get one over root n convergence.
Sorry?
Suppose you need same convergence like MMD.
Uh,
then what is your computation?
Yes, so we can get that whenever L is equal to, so the suggestion we make in the paper is n divided by log n, but anything scalable is with n. And when P in here equals 1, or P greater than 1 with some extra conditions on the nature of it. Yeah, there's definitely a trade-off between guaranteed convergence rate and the cost here. Any more questions? It's great that I had 1 hour. Okay, so we apply EKQD to a bunch of problems in two-sample testing, where we have n samples from one distributions and from the other, and we need to accept or reject the hypothesis that the distributions are the same. So the distances that we consider are a linear approximation to the MMD of cost of n, a MMD multi-approximation to MMD, which is just a partial V statistic of the full MMD of matching cost to the EKQD. And we did match the cost with the constant also. It's not just the asymptotic cost. Just out of curiosity, a very simple dumb estimator of supremum KQD, where we sample from gamma and just take the largest, and just take the direction for which the difference is the largest. The main estimator of interest, expected KQD with n log squared n cost to compute. V statistic MMD estimator of cost of n squared, where n is, should have said that way earlier, n is the number of data points. And this version of EKQD that I didn't really cover in the interest of time, that's to the question that was asked earlier about the origin point. So for this guy, the origin point is the mean, and then we correct for it. And due to the need to compute the mean, it's O of n squared. And actually, it has a very interesting relationship to the MMD, where it kind of sits in between MMD and EKQD. And bottom line for, I will cover the specific experiments, but bottom line, we see that within within a comparable budget of n log squared n, KQD is competitive with MMD even for mean characteristic kernels, meaning the kernels where MMD shines, where it is an actual distance. When MMD is not mean characteristic, we run an experiment that substantiates our theory that KQD can be a distance. And this EKQD-centered object that kind of sits between MMD and EKQD offers the best of both worlds, where it performs well when KQD performs well, and performs at EKQD level when EKQD is better than MMD, and at MMD level when MMD is better. So specifically, this is a synthetic experiment where the two distributions are both Gaussians with diagonal covariance, and the covariances are slightly different, and as the dimensionality of the problem grows, it becomes harder. And MMD is known to struggle as the number of dimension increases on this specific problem. And yeah, we see here that our proposed EKQD does pretty well. Interestingly, slightly better than the centered version, although I wouldn't say that this is definitely significant. What is interesting here is that EKQD is much cheaper than the MMD estimator in yellow. The matching cost MMD estimator is the purple one, and EKQD does much better. The second experiment is the setting that I alluded to multiple times throughout this talk, where we intentionally use a non-mean characteristic kernel to show this as an example. And the kernel in question is polynomial of... Really dislikes me now. The kernel in question is polynomial of order 2, and we compare Laplace and Gaussian that match in the first two moments and not further. MMD, of course, is not a distance in this setting, so all MMD-based methods cannot distinguish between the two distributions, and EKQD can, because it requires less to be a distance. The latter two experiments are less toy and more real-world-ish in nature. Galaxy MNIST is comparing two classes of pictures of galaxies that are of different shape. And here we see that MMD does really well as the number of samples grows. Comparing is easier. EKQD centered, which, as I said, in a way is between MMD and EKQD, matches the performance. And the cheaper EKQD performs better than MMD of matching cost in purple here. And a similar thing happens here, where we compare two image data sets that were made to look similar. So the first one, CFA10, was released in 2012, if I remember correctly, and this one is more recent, and people kind of intentionally tried to put similar images in this one. So this is supposed to be a hard task to tell which came from which data set. And here, again, EKQD centered matches MMD, and the cheaper versions of EKQD, the n log squared n ones, do a lot better than the matching cost MMD one. Yeah, well, I summarized this already. So this is just substantiating the practicality of the method, that if a computational budget is limited, it performs competitively to MMD. Okay, last slide. Cool. Well, thanks for listening. Like I said, the paper for now can be found on my website and will be archived soon. We proposed kernel quantile embeddings and used them to build kernel quantile discrepancies. We established that KQDs are distances under conditions that are strictly more general than those needed for MMD. We proposed an efficient estimator for the expected version of KQD and demonstrated that it's effective on two-sample problems. And, well, this is a new framework. There's a bunch of stuff that could be done next, like kernel selection. We didn't address at all under which kernels this would perform best. Conditional version of the kernel quantile embeddings to match conditional kernel mean embeddings that are used to tell apart conditional distributions, and, well, applications beyond two-sample testing.
So we have time for questions.
Can these quantiles be viewed as quantiles of a Gaussian measure with the associated covariance kernel?
Interesting. Gaussian measure with the associated covariance kernel. So you're suggesting taking that covariance embedding, plugging it into the Gaussian measure on the RKHS? I don't know. We should chat about it. I have no idea. The construct that you're describing, I am familiar with it, but not like intimately familiar, so I'm not sure. Yeah.
Yeah, you could check in the finite dimensional case already.
Yeah. Yeah.
Like two naive questions because I'm not an expert in NLP or whatever, but I was wondering, so here you gave the cost in terms of n, but not in terms of the dimension of x.
Yes.
How does it enter in the story?
That's because of the slicing. In sliced Wasserstein as well, you get a cost that's in terms of the number of slices. So we are able to drop the cost in terms of, oh wait, sorry. So what we don't include in computational cost is cost of computing the kernel. Yes, sorry. I started answering a completely different question. Yeah, it should probably, it should definitely be scaled, the whole thing, by cost of computing the kernel. I guess it's not relevant to these experiments because we compute the kernel for all of these methods. But in the paper we also have comparisons to sliced Wasserstein, in which case, yeah, it is unfair. We should add a comparison with kernel computations, which, yeah, it should be a D-scale. Yeah, thanks.
And then, so at some stage you mentioned that there was this paper that were using the sort of max version of your approach.
Yes.
Did you try it in practice or compared to yours?
We kind of failed at running their code, but we some of the experiments that we ran essentially taken from their paper. This one, I think here is just this one, and the performance that they report, even with the more expensive method, is lower than we have here. But this is just based on what they report. For proper comparison, we should really run it. But I want to highlight that their method is n cube log n, so a lot more.
I was just out of curiosity whether they were performing better, even though at a higher cost.
Yeah, the reported ones were not, but we should really run within the same environment to say confidently.
In practice, what is the size of L you choose?
Different in each experiment. Okay, well, trivially here, it grows from 100 to 10,000, here 100 to 2,500, and here 100 to 2,000. This, I think it's capped at 2,000? I think it's that.
So the number of samples is n, or the number of samples is L?
The number of samples is n. The L is the number of slices, the number of directions, where in these experiments we keep it equal to log n everywhere. This cost of, well, we could have measured here, but we didn't. We kept it to log n everywhere, and the cost of O n squared here is just due to the need to compute MMD.
But did you try, suppose if you keep increasing the L, let's say computation is not a bottleneck for you, but if you keep increasing the L, did you actually see increasing the
we haven't. No, that's interesting.
Okay, so thank you very much again.